Okay, so let's take a look. So hopefully again, you know that it's all about really the H plus in this case, right? Question is, do you put it on or do you take it off, right? So that's the important question. So this is a good time to sort of think about what we talked about earlier, which is we have on the left-hand side our acid, we have our base, right? And on the right-hand side, we have our conjugate acid and our conjugate base. And as we talked about, if it is the acid on this side, its partner would be the conjugate base. And if it's the base on this side, its partner here would be the conjugate acid. So in this case, to help us decide whether or not we should kind of like put the H plus on or take the H plus off, we could think about it sort of backwards. And what I mean by that is if I am looking to write the conjugate base, so that means I am looking to end up here. If I go backwards, that means everything that I am looking at in this case is going to be a Bronsted acid. So at this point, all we have to do is just take the definition of an acid, which is something that will donate an H plus, right? So that means we're going to take the H plus off. So definition of an acid is it will donate the H plus. That means in each of these cases, we want to remove the H plus. So if you know what you want to kind of end up with, either the conjugate acid or conjugate base, kind of go backwards and go, okay, that's an acid I'm starting with, or that's a base. And then all you have to do is just follow the Bronsted-Lowry definition of what an acid or a base is. So that means we're going to just simply take off an H. That leaves me in this case an H and an S. It was neutral to begin with, right? So as we've been talking about, the plus is also important here. So when I lose a positive, I become one more negative. So I went from neutral to -1 in this case. So the conjugate base here would be HS minus. Now, if we're starting with HS minus in the second one, again, we're going to remove the H. That's going to leave me an S. And again, I started at -1 and I lost a positive. So I become one more negative. So I go from -1 to -2 in this case, right? If I look at the next one here, once again, we're going to lose a hydrogen. So that's going to leave us one nitrogen and two hydrogens. Once again, we were neutral to start with. So when I lose that positive charge, I become one more negative, and the charge becomes that. And lastly, here, I'm going to lose a hydrogen. That's going to leave me a hydrogen and an SNO3. And once again, it was neutral to begin with. So it will become one more negative in this case. Any questions on any of those there? Now, let's just say we started with something like HCO3 minus. Why don't you write the conjugate acid for that, starting with it? And why don't you write what the conjugate base would be if you started with it? So in each case, you're going to start with this guy right here, a little bicarbonate. Write the conjugate acid, R the conjugate. Okay, so once again, we'll start here. How about the conjugate acid? Again, we know it is, are we putting it on or taking it off? So if you weren't sure, we could go to our conjugate acid. And again, if I follow my kind of pathway back, I see I end up with a base in this case. And again, the Bronsted-Lowry definition of a base is it will accept the H plus. So that means we're actually going to add the H plus into here, right? Put it on. And in that case, that will give us two H's and a CO3 plus 1 and -1 equals 0, right? So that zeroes us out in terms of our charge. We become one more positive, goes from -1 to 0, basically no charge and neutral. Any questions on that one there? We go conjugate base, just like we did in the problem. Conjugate base, following it backwards, tells us it's an acid in this case. So in this case, we're going to donate an H plus. So we're going to get rid of an H plus in this case. And again, when we get rid of that H, we're left with a CO3. And once again, we're starting negative and we lost the positive. So we become one more negative, goes from -1 to -2 and make carbonate in this case. Yeah. Any questions on that there? Yeah. So if you're ever not sure, because sometimes problems won't tell you, hey, these are all acids, what's the conjugate base? Or, these are bases, what's conjugate acid? If they just tell you, hey, write the thing for the conjugate acid or conjugate base, just think about backwards, use the definition of the acid or base and just either put it on or take it off. Any questions on acid conjugate base pairs? All right, so let's talk a little about acid strength. As we sort of touched upon briefly, in the forward reaction of acid and water, it will produce H3O plus and A minus. In certain cases, those guys can recombine and go the other way, and we get a weak acid, which is what this is. And we know again it's weak because we see both arrows, which tells us it's a weak electrolyte. So weak acids and also weak bases are weak electrolytes. Strong acids and strong bases are strong electrolytes. They're the one-way arrows. Everybody's breaking apart. Now, if the forward reaction predominates, we end up with a strong acid. And as we talked about, since it is a strong electrolyte, going to 100% break apart. So that list that we put up earlier still applies, obviously, here. And again, as I mentioned, kind of a good list to know. So in case you come across it somewhere, you know that you're dealing with a strong acid. And also, as we also talked about, by process elimination, if it's not one of those, then you know you're dealing with a weak acid. Uh, a weak acid, for example, hydrofluoric acid is a weak acid. I think we talked about when we were doing electrolytes. So when this breaks apart, it does break apart into H plus and F minus. And in solution, though, it is because it's a weak electrolyte, going to mainly stay together. It's really not going to break apart all that much, but it will break apart a little bit here. So when you look at that beaker, you mainly have HF floating around in there, still together, but still a little bit of ions floating around. And because it's able to produce a little bit of H plus in that solution, it's still considered an acid, but a much weaker acid. Like hydrofluoric acid, acetic acid, which is the main acid in vinegar, is also a weak acid. That's acetic acid. Is a weak acid as well. So like I said, pretty much if it's not one of those six, it's going to be a weak acid. And again, it will pretty much act like a weak electrolyte and mainly stay together, but still able to produce some H plus. And again, uh, that is why it is still considered an acid. There is a relationship, and the relationship of sort of the acid and its conjugate base pair, or the base and its conjugate acid pair, is this. If you have a acid and its conjugate base, if your acid is strong, its conjugate base will be relatively weak. So it's sort of like an opposite relationship between them. And if you have a weak acid, its conjugate base will be relatively strong. Now, when I say it's going to be a relatively strong conjugate base, it is nowhere near a strong base like sodium hydroxide. What it means actually in this context is it has the ability actually to just continue to react with water and affect the solution as being either more acidic or basic as well. So although we kind of use the word strong here, we're not talking about it in the sense of like sodium hydroxide or potassium hydroxide. We're really talking about it in the sense of it's able to actually react with water and kind of affect the pH of the solution. Now, if you have a base and its conjugate acid, it kind of works the same way. If you have a strong base, it will have a relatively weak conjugate acid. And if you have a weak base, it will be a relatively strong conjugate acid. And again, here is nowhere near like hydrochloric acid or anything like that. It just means it could continue to react with water. So for example, if you took something like hydrofluoric acid, that is a weak acid. Its conjugate partner or base would be fluoride, F minus, right? The only difference between those two is 1H plus. So what happens, for example, if you have fluoride in solution, because it's a solution, there's water molecules flying around. What happens is fluoride can actually react with water, and it will actually act as a base, and it will accept an H plus from water. And the result of that is it will produce hydrofluoric acid in solution. But more importantly, in terms of the solution, is it has the ability to produce hydroxide. And because it has the ability to produce hydroxide, it will actually be a basic solution because of that reaction that's happening. This is what is known as a hydrolysis reaction because it involves water. And that is what we're really talking about here is those kind of conjugate partners that are relatively strong. They have the ability to react with water. And because of that, they can, like in this case, produce hydroxide. There are some that can produce, for example, H3O plus, could make the solution more acidic. This guy would make the solution more basic. So that's what we're talking about here. And again, they're not strong like, like I said, like a sodium hydroxide or a hydrochloric acid or anything like that. There's our list of strong acids. And again, more on our list that we have there on the other page. And we already talked about our sulfuric acid that has 2 hydrogens that it can donate, again, one at a time. So as we saw there, we have some amphoteric substances like water. And also, by the way, the example we just did with the bicarbonate is also amphoteric, right? It has an H to give, and it can accept an H like we just did there on that problem. Like I said before, typically if you have something with an H and a minus, it can kind of go both ways, just because, again, it has the hydrogen to give, and it can accept the hydrogen. It has room for it to come in. So again, as we talked about earlier, we saw our water in this case acting as the acid and donating. And in this case, our water is accepting the H plus. Water can even react with itself. So in one case, the one water is an acid, the other one is a base. So one is an acid, one is a base. So in this case, we would be sending our H plus over. And the result of that is we will make H3O plus and OH minus. This is what is sometimes referred to as the autoionization of water, basically water reacting with itself. It's basically what's happening in a water solution. They're just kind of reacting with each other all around. And the result of this is it actually will set up an equilibrium water, and it will give us a relationship because it is an equilibrium that is known as Kw. And Kw is the equilibrium constant for water. Kw is the concentration of H plus times the concentration of OH minus. And when you see those brackets, that means concentration. And basically it means molarity, moles per liter in most cases. And that equals 1 times 10 to the minus 14. That is almost a constant. In reality, it's really not. It can change with temperature, but most of the time, that is the number 99.999% of the time that you're going to use. And then here, probably 100% of the time, that is definitely what you're going to use, which is 1 times 10 to the minus 14. This is one of the first sort of equations that, again, you could use H3O plus in there as well. As you can see down here, Kw can also be written as H3O plus times OH minus equals 1 times 10 to the minus 14. This is really the acid part of the solution. This is the base part of the solution. Same deal, acid, base. And again, remember H plus and H3O plus, basically the same deal here. Now, we could use this to help us determine whether or not a solution is acidic, basic, or neutral based on how much H plus is in that solution versus OH minus. The relationship, by the way, between H plus or H3O plus and OH minus is an opposite relationship. So as one goes up, the other goes down. So as the H plus goes up, the OH minus goes down. As the H plus goes down, the concentration of OH minus goes up. So they always go opposites of each other. So one goes up, one goes down in terms of the relationship. And again, if you have more H plus in the solution, it's going to be an acidic solution. If you have more OH minus in the solution, it is going to be a basic solution. Now, we could use this to calculate, and as I mentioned before, if the H plus concentration, which is basically the acid part of the solution, is bigger than the OH minus concentration, then that solution will be basic. If the OH minus, which is the base part of the solution, is bigger than the acid part of the solution, which is H plus, then it will be basic. If they equal each other, they actually will equal 1 times 10 to the minus 7 molar. There's the M down there. And you will have a neutral solution. The good news is if you need to calculate one of the concentrations and have the other, it is basically the same calculation regardless of which one you're given. You take 1 times 10 to the minus 14 and you divide it by the other concentration that you were given. Now, definitely 100% of the time in this chapter, if you are still not using your exponent button, you're going to be in big trouble. Yeah. So you have a lot of numbers that are in scientific notation, including 1 times 10 to the minus 14. You definitely want to make sure that you are punching in using your exponent number. You will very quickly find out if you are not punching it in correctly. Your answer will look good, but like the exponent part of your answer will be off. Yeah. And that's usually a sign that you're not punching it correctly. So definitely got to make sure you're using your exponent button definitely as you do it here. Any questions on that there? Right. So why don't we try some here? So for each of these, actually let's take 5 minutes and then we'll try this one here. As an example now, so you have either the H plus concentration, which again, a reminder is the same thing as the H3O plus concentration, or the OH minus concentration. So you need to determine the other. So for this one, we're looking for the OH minus concentration. This one also the OH minus concentration. This one the H plus concentration, and this one the H plus concentration. All right, so use our formula there we just saw. Calculate each of those, and then afterwards you need to determine if it's acidic, basic, or neutral, each of these solutions. So take a few moments there and with our exponent button divided by 2.6 to the minus 8. That's going to give us here for our OH minus 3.8 times 10 to the minus 7. Once again, here we do need molarity and as a unit. And here we're going to be comparing the H plus concentration to the OH minus concentration. And really, when you're doing this, you can just really look at these numbers here, the exponents. And when we look at the exponent, as we just talked about, when you have a negative exponent, the smaller negative exponent is the larger one. And that means in this case, the OH minus is actually greater than the H plus concentration because we're going to go 7 places this way and put zeros. Here we're going 8 places, which is more, and putting zeros is going to make a smaller number. That means really the base part of the solution is larger than the acid part of the solution, and that would mean that this solution should be basic in this case. Any questions on that? Again, as I talked about earlier, if you find yourself like this part of the number is good, but this part is just slightly off, it is probably the way that you are punching into your calculator. Also, you remember your calculator may not give you your answer in scientific notation, so you may have a bunch of zeros, and you might have to put it into scientific notation, or write the correct number of zeros, I suppose. So just keep that in mind. Looking at the next one here, we have the OH minus in this case, which means we would be solving for the H plus concentration. And that's going to, again, be our 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 9. Again, punching those in correctly. 1 exponent button, negative button, 14, divide 6.2, exponent button, negative button, and 9, and equals will give us here. Looks like 1.6 times 10 to the minus 6 molar. And again, here we're going to do some comparisons. So we have our H plus concentration and our OH minus concentration. So really, again, the acid part of the solution and the base part of the solution. Taking a look here, that's minus 6, that's minus 9. So again, the smaller negative exponent here is actually the H plus, which means it is larger than the OH minus. And that would mean our acid part is greater than our base part, and this guy should be acidic in this case. Yeah. Any questions on that one there? And the last one on this problem here was OH minus as well, 8.1 times 10 to the minus 3. Again, we're going to solve for the H plus. 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3. Putting that in correctly into our calculator here, going to get us, looks like 1.2 to the minus 12 in this case. Again, that would be molar. Doing our comparison of the acid part to the base part of the solution here. Again, that is minus 3, which is a larger number than minus 12, and that's for our OH minus. So in this case, our base part is larger than our acid part, and that would lead this to be a basic solution on this particular example. Any questions on that one? So again, definitely want to make sure you use that exponent button. Obviously, if you have that calculator we talked about way back when, make sure you put parentheses around every number. Yes, sir. You might be asked that question. It's a very common question, whether or not the solution is acidic, basic, or neutral. Yeah. So again, to determine that with this, and we'll talk about some other ways later that you could probably also determine, but using this sort of information, you want to compare the H plus to the OH minus, and whichever one's larger, will tell you if it's acidic or basic. Yeah. Other questions? Okay. Try a couple more here, just to make sure. I agree, hopefully. Those are the ones we just did. All right. Don't worry about which is greater. Let's just do what is the OH minus concentration here? And again, is it acidic, basic, or neutral? All right, so just like the last couple or few that we did, we're looking for the OH minus, and really if you have the H plus or OH minus, you can go with our KW still, which is H plus and OH minus equals 1 times 10 to the minus 14. So as we've seen, it pretty much the same calculation regardless of which one you're given. So once again, we'll go 1 times 10 to the minus 14 up on top. Pretty much a constant value you always have, divided by our one that was given, 2.8 times 10 to the minus 5. Again, making sure to use our exponent buttons here. We'll get us something, maybe. Let's see. That looks like maybe 3.6 times 10 to the minus 10 molar in this case would be our hydroxide concentration. And now in terms of comparison, we're comparing the H plus to the OH minus. And in this case, our H plus is to the minus 5. Our OH minus is to the minus 10. And again, minus 5 is the smaller number, which means it's the larger number in this case. And that belongs to the H plus, and the H plus really is the acid part. And that means that this solution should be acidic, as we have more free H plus ions floating around that solution than we do OH minus. Any questions on how to calculate H plus or OH minus using KW? Okay. All right, so I think we'll skip this one. It's kind of the same idea. We're now going to talk about another sort of aspect of a solution being acidic or basic or even neutral. And that is the pH scale. And the pH scale is a common way that we do it. By the way, this is not negative, it's just from PowerPoint. And to calculate the pH, we take the pH is equal to negative log of the H plus concentration. Again, this is another formula where you can, if you want, substitute in H3O plus. Again, it's really the same thing we're going to put in there. Now, when we talk about the pH scale runs from we'll go 0 to 7 to 14, and less than 7 is acidic, above 7 is basic, and 7 right on the nose is actually neutral, and that is the case where our H plus and OH minus equal each other. And if you were to calculate the pH at that point, you would have a pH of exactly 7. So we're going to go with 7 on the nose there is neutral. Anything slightly above 7 will be considered slightly basic. Anything less than 7 will be slightly acidic, unless it's, like 7.0 0.01 or something like that, then you could call it 7 or 6.99 or something like that. But anything a little bit above that or a little below that, we will go with being acidic or basic. As you go from 7, sort of your middle point there, if you go towards 0 on the pH scale, it becomes more acidic. And if you go from 7 towards 14, it becomes more basic as you kind of go in that opposite direction. So as I mentioned before, the name itself actually tells you what you need to calculate it. So when you see pH, it tells you basically you need the H plus concentration to calculate it. That is negative log of the H plus. So depending on your calculator as to how you will punch this in, if you have a display calculator, you will punch in your negative button, your log button, and then you'll do your H plus concentration and making sure you probably use your exponent button in that process. If you have a non-display calculator, this formula and others we will see shortly, you need to go backwards. So you need to actually start with the number or the concentration. You then need to hit the log button. And then you need to basically hit your negative button to make it positive. So if you have a display calculator, you're going to punch it in just like the formula. Non-display, you're going backwards. If you're not sure which type you have, just hit the log button. And if it says log on your screen, congratulations, you have a display calculator. If you hit the log button and it says error, congratulations, you have a non-display calculator. And so that's a quick way you can very much determine that. So if you hit log and it actually says log, then do it the display way. If you hit log and it says error, do it the non-display way. All right. So again, you do need the H plus concentration to calculate that. And let's talk about the significant figures with pH. And the number of decimal places you should have in your pH type of calculation should be equal to the number of significant figures there are in the concentration. So whatever the number of significant figures there are in the H plus concentration, you want to use that to determine how many decimal places, not significant figures, but decimal places your pH value should have. So just to make sure everybody's calculator is working. Let's calculate the pH here to the proper number of digits. And also, is it acidic, basic, or neutral as well? So take a moment, grab your calculator. Again, make sure you know how to punch it in. Go one of those two ways, depending on your calculator. All right, so let's take a look. So again, obviously we're using our pH formula, which is negative log of the H plus concentration. pH means I need the H plus concentration, or the H3O plus concentration, same thing. So again, depending on your calculator, if you got the display calculator, you should probably punch it in like this. You should again hit your negative button. You should then hit your log button. You then should type in 1 and your exponent button, then your negative button, and 5, and hit equals. You have a non-display. You should start with 1 and your exponent button and your negative button and 5. You then should hit log, and then you should hit your negative button one more time for good measure. If you do any of those things, hopefully staring at the screen on you is a 5. I hope, yes, that's on everybody's screen. All right, so now we got it calculated, hopefully right, depending on which way you're going there. Now we need to give the right answer. So should it be 5? Should it be 5.0? Should it be 5.00? Which is the correct way to give that pH? So the rule is the number of significant figures in the concentration. So how many sig figs does this number have? That's 2 sig figs. Is how many decimal places there are? 2 decimal places. This would be the correct answer, yes. So we're going from significant figures to decimal places as you go from concentration to pH. And by the way, it goes backwards. We'll talk about how to do it shortly. But if you're going from pH back to concentration, you go from decimal places to significant figures. So it works both directions. So this would be the correct way, 5.00. Again, 2 sig figs in the concentration, 2 decimal places in the answer. Yeah, question on that. By the way, is it acidic, basic, or neutral, this one? It is acidic. It's less than 7. By the way, when you are asked that, is it acidic, basic, or neutral? There is just one answer for that. Yeah. So not acidic or basic, acidic and basic. I've never had anybody give all three, acidic, basic, and neutral, which I think is good. But I have had people give acidic and basic for the same solution. So it's got to be only one answer for that. Yeah. Not all 3 or 2. Any questions on how to punch that in there? Okay. All right, so let's try some here. 2 different solutions. First one, we got an H plus concentration, 2.1 times 10 to the minus 5. What is the pH? And next solution, OH minus 5.9 times 10 to the minus 8. What is the pH in each of them? And in each of them. All right, let's take a looky. We got H plus concentration there, which is good because that's what's needed to calculate the pH minus the log of the H plus concentration. And that means if I put it right in, minus log of, for the first one there, 2.1 times 10 to the minus 5. Again, you want to obviously punch it in according to your calculator. And if you do that on your calculator there, going to get you a 4 point, call it 6.8 pH. Once again here, 2 significant figures, again, 2 decimal places, yeah? This would be acidic, basic, or neutral. This should be acidic, again, less than 7 in this case. Any questions on that one there? All right, so here on the second one, we're looking for the pH, which is minus the log of the H plus concentration. Again, it tells you I need the H plus concentration, but that looks like the OH minus concentration. So maybe I use my KW we used previously to get to my H plus concentration. 1 times 10 to the minus 14 divided by 5.9 times 10 to the minus 8 will get me get me something with a lot of zeros now. So it gives me something like I'll go 1.7 times 1.7 times 10 to the minus 7 molar. Now that I do have the H plus concentration, now I can use my pH minus the log of that. Again, making sure you punch it in correctly. That's going to give me a pH of 6.77 in this case. And again, that is going to actually be slightly acidic as well. Now, if you just rolled right in and did your minus the log of 5.9 times 10 to the minus 8, you obviously did not calculate pH, right? Because that is not the H plus concentration. That is the OH minus concentration. The good news is, you did calculate something. So not pH, but since that's OH, you calculated what is known as the POH, yeah? And the POH is minus the log of the OH minus concentration. So if you did that, you ended up with something, if I hit the right button on my calculator, maybe, minus 8. You ended up with like a 7.23. Which again is not the pH. That is what is known as the POH because you use the OH minus concentration. But not all is lost, as we will see in a slide or two, just a couple of slides ahead. The pH plus the POH actually equals 14, which means if you take your POH and take 14 minus your 7.23, you will get your pH. So you could have just went that way as well without having to use KW. You're just a few slides ahead, I suppose, even though maybe you didn't know you were as well. So if you happen to have done that, it is definitely not the pH, but it is something, and it's known as the POH, and it actually is quite useful because as you can see there, you don't actually have to use KW like we did in the problem. you could actually do that. Or it also illustrates that you could definitely still use KW if you wanted to, and you'll get the same answer. So there's actually a few different ways you could kind of get to that. As to an earlier question, there's sometimes different ways you could kind of figure out if it's acidic, basic, or neutral, depending on what you calculated. Any questions on that there? Yeah. That's what we just did. So the pH scale is based on the log of 10, and really for every one sort of power of 10 that you move, the pH basically changes by 1. And by the way, for example, like the one we had, 1 times 10 to the minus 5 is a pH of 5. If you had 1 times 10 to the minus 3, it's a pH of 3. 1 times 10 to the minus 4 is a pH of 4. So every power of 10 that you change, a pH unit basically changes with it. As the H plus concentration increases, you have a lot more H plus in the solution, which means your pH will become more acidic and go down. If you have a lower H plus, that would also mean that your OH minus is higher. And here, this would mean your OH minus is lower. And your pH will start to go upwards towards the basic area, right? Because again, you're having more OH minus than you do H plus in that solution. So again, opposite relationships between H plus and OH minus, but again, the more free H plus you have in the solution, the lower the pH is and the more acidic it is. That is why what we were talking about earlier when we talked about strong acids like HCl, when that goes again for a swim, it's going to 100% break apart into these guys. And what that's going to do is just have a lot of free H plus. That's going to make your H plus concentration really high, and it will drop your pH and make it more acidic than it would if you had something like a weak acid, which won't produce as much free H plus. And you will still be acidic for the weak acid, but it will be a higher pH in the acidic range than, say, maybe something like hydrochloric acid. Any questions on that? Yeah. Now, there's a couple different ways you can measure pH. On the left, there is a pH meter. It's actually an electrode, and it measures the H plus concentration that's floating around in that beaker. Honestly, what you do is you calibrate it, it does voltages, and it makes like a calibration curve, and you tell, hey, this voltage is like a pH of 7, this is like a pH of 4, this is a pH of 10, makes like a little straight line, and then you put it into your solution, go, cool, that voltage is here, that means that pH is this value. Nice thing about it is it just spits out to you there right on the screen, the pH actual meaning of it. You could also use pH paper, which is over here. If you ever like tested a pool or something like that, that's kind of the same idea. You get the thing kind of wet with the solution, and then it changes colors. You kind of match it up to a key. Not as accurate, right? Because you kind of try to find the right color scheme, and they tend to always fall like between things and like to figure it out. Now, these are two common ways you can figure out the pH. We also sometimes will use litmus paper, and it does not tell you the pH, but it will tell you if the solution is acidic or basic. So if you use litmus paper and you put some solution on it, and it turns red or stays red, it's acidic. And again, it doesn't tell you the pH. But if your litmus paper turns blue, it will be basic or stays blue. And once again, it doesn't tell you the actual pH, but just tells you is it acidic or basic, that solution. So here's the pH scale of some common things. We have pure water at 7. We have a strong base, sodium hydroxide, way up there towards 14. Strong acid down towards 1. Stomach acid, vinegar, and so forth. Cleaners up here in the basic range. By the way, if you take water, and especially water has been out a while, will the pH be 7? No, it'd be probably like in this range down there, somewhere in that ballpark. And that's because it'll pick up some CO2 from the air and create some carbonic acid, which is an acid, which means it will then release some more H plus and lower the pH in that particular case. So sometimes people are surprised. They look at, whoa, it's not 7, but especially if it's been out a while, it picks up a lot of that. It'll increase the H plus that's in that solution and actually lower the pH a little bit. All right, so we kind of jumped it on that last example, but there are definitely similar scales to pH, and one is the pOH scale. And much like the name implies, it uses the OH minus concentration And that is the pOH. And again, the nice relationship between those things, we could add our pH in here, minus the log of the H plus. And again, our pH plus our pOH equals 14. While we're at it, we could add our KW that we saw earlier as a way to do some of these things. So you do have a few different options depending on sort of what information is given to you and sort of which way you want to kind of roll with it. As long as you choose any of them, they should get you to the right place. By the way, the pOH scale does run opposite of the pH scale. So the pH scale 0, 7, 14, again, acidic and basic, again, neutral. On the pOH scale, also runs 0, 7, 14, but it is opposite. So this is basic, this is acidic, and this is neutral. So if you have a low pH, you will have a high pOH and vice versa. So they're opposite of each other. I personally would always look at the pH scale because that is the scale everybody has in their head. I would probably not look at the pOH scale as it runs opposite of it. Earlier, I said sometimes people will give it's acidic and basic in the same answer. And this is why, because they will calculate the pH and it'll go, cool, it's over 7, it's basic. Then calculate the pOH and go, cool, it's below 7, it's acidic, the same solution. Yeah. So they are opposites of each other. So it's a very common error that people make when they do that. So when you're looking at whether or not it's acidic, basic, or neutral, I would just strictly stick with pH and use that. Probably easier in comparing H plus or OH minus concentration. You could also do that like we did earlier, but definitely I would stick with the pH scale. That's usually the one everybody has sort of in their head. To add to this sort of list of sort of calculations that we also can do, and that is if you actually have the pH, you could get directly from that the H plus concentration. So if you're given the pH, and again, the name tells you pH means you could actually get the H plus concentration from it. And to do that, that is the inverse log of the negative pH. Now, the inverse log, when you punch that onto your calculator, is a 10 and a caret. And you want to make sure it's negative pH. It's also how a lot of people do scientific notation incorrectly. So to get to the inverse log, on most people's calculator, upper left corner, you have a second button, or maybe got a shift button up there. And then you usually have a log button somewhere that has like a 10 and an X on it or something like that. You hit the second or shift button, then you hit the log button, and it will pop up that 10 and a caret usually on your calculator. And that definitely is what you want to use it for. Hence why you do not want to use that for scientific notation, because you're then going to mess your answer way up as you do it twice. Now, by the way, this is still the same deal. If you have a non-display calculator, you need to work backwards with this equation. If you have a display calculator, you can work forward. With that, if I have the pOH, as you could probably imagine from the pOH value, you can get directly the OH minus concentration. And that also is the inverse log of the negative pOH. And again, on your calculator, that's probably going to pop up something that looks like this when you do it. So again, how do you do it if you need to that way? pH plus pOH equals 14. So to punch these in, either of these equations, they're both basically both the exact same calculation. If you have a display calculator for those guys, you would hit your second or shift button, you would hit your log button, and then you would hit your negative button and either the pH or the pOH, whichever one you're kind of putting in there. If you have a non-display calculator, you need to actually start with the pH or pOH. So you're going to put the pH or the pOH in there. You then need to hit your negative button to make it negative. You then need to hit your second or your shift button and then your log button. So that is the way to do either of those calculations, which are basically both the same calculation in terms of punching it in. Any questions on that? So this page has pretty much all the calculations here, right, in this chapter. And again, it does give you, like I said earlier, some different ways that you could get to the same answer, regardless of which way you choose. Again, they all should get you to the same answer, provided obviously you punch it in correctly and do the math part of it correctly. So let's take a look at ones here before we wrap it up-ish. All right. So why don't we just make sure everything works here? So let's just do maybe the first one here. It's not the first one. For the first one here, what is the pH? What's the pOH? What's the OH minus concentration? And is it acidic, basic, or neutral? So take your choice of whichever way you want to do those, but end up with those answers and see what you come up with. Okay, let's take a look since we're getting to the end here. So basically we're given the H plus, and it does open up really two pathways depending on how you want to do it. Obviously, we have the H plus, so you could obviously use KW like we've done previously, and that could get you to the OH minus concentration. We obviously have the H plus here, which means we could also go right into our pH equation. So again, you have a couple of different ways, and neither one's better than the other, just sort of your preference as to which way you want to go. I'm going to actually do the pH first, so that's what I'm going to choose to do. I got a pH here minus the log of 3.6 times 10 to the minus 9. And if I pop that in there again, whichever way your calculator needs you to punch it in, make sure you do. -9 here, it looks like. And that's going to give me an 8.44 as my pH in this case. Now, at this point, you have also a couple of options. You can, because you have the pH, you could get the pOH because that would equal 14 minus the pH. You also could get the, well, you don't really need the H plus since you already have it. So you could go that way. So that's what I'm going to do. You could also, if you still want to go back and do KW to get the OH minus, you could do that as well. But I'm going to get the pOH here. So the pOH would equal 14 minus 8.44, which seems like a pretty easy way to get to the pOH. So I'm just going to subtract 14 basically and a 5.56 for our pOH. Again, you still have the option of going back to KW to get the OH minus, or you could use that calculation we just talked about, which is now that I have the pOH, I could get the OH minus. So that's the way I'm going to do it for here, just to show you the calculation. So the OH minus here will equal the inverse log of the negative pOH. And again, on your calculator, once you punch it in properly, it probably will pop up a 10 and a caret, and you want to make sure you make a negative 5.56. Once again, if you're going to punch this in, if you have a display calculator with this particular one, you would do your second, your log, and then your negative and 5.56 and hit equals. If you have a non-display, you would start with the 5.56, hit your negative button to turn it negative, hit your second button or shift button, and hit your log. And whichever way you need to do it should hopefully get you there. And if you do that wherever it just went there, or on my calculator, if I could find it, there we go. I get an error. That's probably not so good. When we try that again, that would be that button is what I'm looking for. There you go. Negative 5.56. That's going to give us a OH minus of 2.8 times 10 to the minus 6 molar in this particular case. Any questions on calculating that way there? Again, you could also alternatively, like we talked about, do that the OH minus is equal to 1 times 10 to the minus 14 divided by 3.6 times 10 to the minus 9, and that would get you there as well. So pretty close. Now, lastly, right, is this acidic, basic, or neutral? This one is. It is basic. I want to look only at the pH, and that would mean that it is basic in this case. Again, not more than one answer on that particular question. Any questions?